We're going to look at what's called the matrix of derivatives. So this is, if you know about the multivariable chain rule, but we're going to look at a more sophisticated version of it. And then it's going to have to do with things like change of variables or integrals. So we've got a function. Z is a function f of xy. And I'm just going to leave that abstract for now. But then x and y depend on two other variables, let's say u and v. And I'm making that more explicit. So x is u cosine v and y is u sine v. And that relationship we're going to call G. So here's the tree diagram you would build for that. Z depends on x and y, x depends on u and v, y depends on u and v. And so here, to be really explicit, f is a function from R2, from the plane to the line, just one output. G is a more interesting gadget. It takes the two variables u and v and spits out the two variables x and y. And I'm going to make this very geometric pretty soon, maybe in the next video. But right now, I'm not going to emphasize that too much. It's going to be super crucial to be geometric very soon, but I want to see what we can get just by looking at the multivariable chain rule in this situation and being kind of clever about how to write it. So the multivariable chain rule tells us if we want to know how z depends on one of these initial variables, not the intermediate variable, but if we know how sensitive z is to each intermediate variable, we multiply that by how much the intermediate variable is actually changing, or how fast it's changing with respect to u, and then we sum over those intermediate variables. Ooh, that's not a z, that's a y. And similarly for v, dx dv plus dz dy dy dv. Okay. And I'll put in the explicit stuff in a minute. But I just want to point out that this might look sort of familiar, that the output, I'm combining two things, something to do with f, something to do with g. In the output, there's two numbers in the output, and each time it's a multiplication and addition. It's like pairing two things, multiply, pair two things, multiply, and then add those multiplications. Similarly for here. Well, that is exactly matrix multiplication. And I want to show how that comes out of matrix multiplication. So what we're going to do is we're going to look at, I'm going to say that, let's see, which way do I want to do it? Okay, I want to say that the matrix of derivatives of G, and that's going to be capital DG. Sometimes people just say G prime, because it is really the natural generalization of the derivative of one variable. I'm going to call it capital DG, is just recording all the partial derivative data that we could actually be interested in for G. It has two outputs and two inputs. So I'm going to record dx du, dy du, dx dv, dy dv. And it's natural to put it in, just like with any matrix thing, as the different outputs correspond to the rows. So x output of G corresponds, oops, that's going to be a V, corresponds to the first row, and the inputs correspond to the columns. So for example, this is the second output in the order that I happen to be running. Write this in, and the first input, so that goes in the second row, first column slot. Okay. And I'm also going to look at the matrix of derivatives of f. Well, now that has two inputs and only one output. So that's going to be dz dx and dz dy. That might look familiar because that when you pack, we've got a slightly different way of packaging that up called the gradient, and I'll talk about the relationship of that in a minute. Okay, so what can I erase here? Okay, so what is this about? What is this calculating? This is how z depends on u and v, or in other words, it's about the derivative of f composed with g. And so the derivative of f composed with g, well, let's see. Oh, yeah, I shouldn't erase that one thing. F composed with g, that goes from R2 to R2 through g to R1. It just has two inputs and one output. So it's just a direct, it's the combination there, thought of as one machine combining these two machines from R2 to R1. And so that is going to be, okay, if I forget that it was made by two machines and just think, hey, it's how z depends on u and v, and somebody doesn't tell me it was created with these intermediaries, okay, the matrix of derivatives there, just a convenient way to package these derivatives, that's going to be dz du and dz dv. Okay. And this, I claim, is exactly a matrix multiplication statement. Because, what is that? dz du is going to be kind of long. Well, it's going to be all this stuff, right? Actually, I'm not even going to put it in. And that's all this stuff. And I'm going to have to erase something. Let's erase this. Don't think we need the tree diagram anymore. And I claim that's exactly what we'd get if we took dz dx, dz dy as a row vector, a 1 by 2 matrix, and multiplied it by dx du, dx dv, dy du, dy dv. Let's see. So dz dx, dx du, bingo, plus dz dy, dy du, bingo. And that row matched with that column, kind of a dot product, that shows up. That's this guy, and that's going to show up here. dz dx, dx dv, dz dy, dy dv. So that row dotted with that column, that gives us this guy, and that shows up here as advertised. Okay, so we get a beautiful, beautiful statement of the multivariable chain rule, at least in this case, and in fact, quite generally, quite generally, it's that the derivative of a composition is the matrix product of the matrices of derivatives. That is very sweet. Very, very, very sweet. Okay, so let me get a little more explicit. And remember G here, G, we had x equals u cos v, y equals u sine v. And so the matrix of derivatives here, dg, at an arbitrary point, dx du is going to be cosine v, dx dv is minus u sine v. Dy du is going to be sine v. Can you see that? Yeah. And dy dv is going to be u cosine v. And so in our chain rule calculation, let's see, where do I want to put it? I think I'm just going to erase everything now, kind of restart. Okay. And so this very, very elegant way to say the chain rule is going to say that, again, that dz du, dz dv, I'm going to calculate them both at once, because you always need them both. Well, it's most of the time. You don't usually want that in isolation. Is just going to be take how they depend on x and y, and then multiply them by this matrix. So, for example, now there is a subtlety, same subtlety we always have, which is that these dz dx have to be calculated at the right point. This has to be evaluated at x of whatever u and v you're interested in, and y of u and v, whatever you're interested in. So let's do that. Let's suppose, and then that'll be plenty for this video, suppose that that dz, that at, let's say, 2, let's say, oh yeah, let's say 2 comma 2, xy equals 2 comma 2, dz dx is minus 3, and dz dy is 4. So increasing y is a good thing for z, increasing x is a bad thing for z. We could talk about what the gradient would look like there if we want to, but maybe I'll say that in the next video. Calculate dz du and dz dv at I claim we can calculate it at u equals 2 root 2 and v equals pi over 4. Not 2 comma 2, because these are x and y values. So why did I come up with those guys? Because x of 2 root 2 pi over 4 is 2 root 2 times cosine of pi over 4, which is 1 over root 2, which is 2. And similarly, y of 2 root 2 pi over 4 equals 2 root 2 times 1 over root 2 equals 2. And if you hadn't cottoned on to the fact that these are secretly polar coordinates, that's probably becoming somewhat more obvious now. Okay, so we've got in x and y, we've got this point 2, 2, and we know that going this way tends to increase our variable z. So you could think of it as maybe temperature or something like that. And going this way tends to decrease the temperature, the z variable, whatever you want to think of it as. And I want to know now and then the x and y, they depend. I'll give you a little hint as to how we're going to think about it next. We're going to think about this as there's going to be a transformation. Think about this idea of x and y depending on u and v very geometrically. We want to think of this as a transformation. And over here, it's u is 2 root 2, v is pi over 4. And we're thinking of that point as transforming over to here. And we're really thinking about how does z, okay, and then this goes to z on the real line. We're thinking about how does this quantity, because it depends on x and y, and because x and y depend on u and v, how does z change when I change u or v? When I go this way in u and this way in v, that's going to do something more interesting in here, and we'll talk about exactly what it does. And how does that affect z? Let's just look at the numerical calculation, though, first, before we get into the geometry, even though I love to privilege the geometry. Okay, we're just going to take dz dx minus 3, 4, that matrix. And then, I erased the matrix. Let me put it in here. It's cosine v minus u sine v, and we're going to make that numerical to make it very explicit. And then sine v u cosine v. Okay. And so that's going to be minus 3, 4. And now we're going to make that, we're going to plug in the u and the v. So cosine v is just 1 over root 2. Minus u sine v is just going to be minus 2. Sine v is 1 over root 2. And u cosine v is, that's just x, really. And so that's just 2. And so we multiply those matrices together. We don't get anything super pretty because of the 1 over root 2's here. But we're going to get minus 3 over root 2 plus 4 over root 2. So you're going to get 1 over root 2. And then 6 plus 8 is not that bad, 14. So that's a very explicit example of, and it's really just recapitulating the chain rule. We've really phrased it in an elegant way, and so that it's going to make all chain rules ever the same rule. But I don't want you to think that this is a calculation we couldn't have done before. But it unifies all the chain rules in a beautiful language, and it's my real interest in it is it's going to look at this idea of like transformations and changes of variables from like the plane to the plane. It's going to be incredibly useful for thinking about that. And then that's going to lead into change of variables for integrals. But that's plenty for one video.